Good day, everybody. We'll be looking at connections, and when I mean connection, I mean both thread and welded connection. And if time permits, we'll look at splice. So when we say connection, most of the failure in structures always occur around the, let me say 30% always occur around the joint area for the member. For instance, maybe where it's being joined, one plate is being joined to another, and this is an example of a fillet welding, or this is an example of a bolted joint. So we'll look at the design of this member using welded joint or using bolted joint. You already know what a gusset is. This is a gusset, like a plate where we join our members together. And another thing that is worth knowing is the bolt type we are using. You know, bolts, they have different sizes, different type. Maybe is it black bolt, friction grip, etc. So now let us start with welded connection. Most welded connection is now done using electric arc welding, where a welding rod or electrode is fused to the parent metal. Now this is an example of as I said the other time, this is an example of a welded joint. Now let us continue with what we are saying. Now in this welded joint, there are two basic types of weld. We have the fillet weld, and we also have the boot weld, as shown in figure 11b, A and B, exactly as I explained to you. Now let us now look at how this welded joint is being carried out. A weld which passes through the whole thickness of the parent metal is a full penetration boot weld. Now, and provided the correct electrodes are used, it can still be assumed that the weld is at least as strong as the parent metal. That is, when the welding joints are well done, the both material, they behave like the added material behave like the parent one. The fillet welds, they are classified in terms of their leg length, as shown in level 3. The figure 11.3, yeah, you can see this is the leg length, that is from the member to where the something is, and this is the throat here. This is the throat. So we'll be doing some calculation on that. Now, how do we know the throat size? The throat size is leg length times cos 45. Throat size is leg length times cos 45. This is angle 45. So which is equal to 0.7 times the leg length. Because of the importance of the throat size, a finished weld should always be convex in shape. The design strength of a fillet weld is in S275 steel is as follows. That is, the design shear strength is this: Fu over root 3 divided by beta W gamma M2, where gamma M2 is the partial safety factor, which is 1.25, and beta W is 0.85. Now this above, by the time we put all these, substitute these values, substituting this one here, substituting B and M, Y, gamma M2, this above equation reduces to 0.54 Fu in Newton per mm square. That is, the design shear strength is this. This is the formula for your design shear stress. Now, the design resistance per unit length is the design shear strength multiplied by the throat thickness. That is this one multiplied by the throat thickness. And as you know, the throat size is this over 7 times leg length, which is over 7 times leg length. So definitely our design shear strength will now be equal to this. If you multiply this by this, you have 0.38 like that. Now figure 11.1 shows the above for typical weld leg length with F equals to 410 for S275. Now, depending on the leg length of the in millimeter, the strength varies. Now look at the leg length here is 4. Under 4 mm, the strength is 0.62. When we have a leg length of 10 mm, the strength is 1.55, etc., etc. Now you can see the way the plate is, how each member is being joined. Look at how the bolts are joined and things like that. Now there are built up being fabricated from welded steel plates. That is, when we join them together to make a different member that is not in size, they are built up. That is, you are building it up. Now, for instance, there are times that we have a span that is not covered in the market sale. They don't have that particular size, so we have to make sure that we fabricate those member and then put all the necessary things into consideration. Now, unless a weld forms a continuous loop, the length of a fillet weld is often reduced by two throat lengths to compensate for the defective welding at the start and the finishing. Now let us just look at an illustration on how this leg length is being calculated and things like that. Let's say, for instance, we have an angle plate 80 by 80 by 8 angle welded to a gusset plate. Now that's in figure 11.4. This is 11.4. Now we have this member 80 by 80 by the thickness is 8 mm. Now it is to support a tensile design load of 300 kilonewton. If it is welded all round up with a 6 mm fillet weld, what is the required leg length L? Now the first thing we'll calculate is, we first look at, okay, what is the thickness here? 6 mm. What is the strength? The strength here is 0.93. You take that out. The weld strength is 0.93. Having done that, then we'll look at the required length. The required length is the design load all over this, like the way we calculate our force per unit area. Now this 300 divided by 93 will give us 323. That means we need a total leg length of this. Now if we have a total leg length of this, now let us look at the member. We have 80 by 80 by 8. So if we have 2 times 80 plus 2L, now to be equal to the total length, the length L will now be equal to this 323. If you make it the side formula, minus 160 divided by 2 will give us the length and the leg length. Now the question that I may be asking is, how did we come about this 80? This is this 80 coming here, and what else do I need to talk about? I think that's all on that. That's all. For me, everybody should be able to calculate this particular illustration out. Now let us go to bolted connection. Now we have there are two basic types of bolts, and they utilize different basic principles to support a load. We have the bearing type load and preloaded bolt. Now the bearing type bolt, it depends for their strength on contact between the bolt shank and the side of the hole in the places to be fused. Now as you can see in 11.5a, this is an example of the bearing type bolt. But however, the preloaded bolt or the friction grip bolt are tensioned so that they clamp the plates together. friction developed between adjacent faces, as seen in figure 11.5b. You can see. So let us look at boats. They are generally fitted into holes which are 2 mm larger than the boat diameter. Why are we doing that? So that we have whatever boats we are using, there must be a tolerance so that it will be able to enter. So this 2 mm is used for the tolerance, and this allows a certain amount of adjustment when the steel is erected, and fabrication tolerance can thus be accommodated. Now, for smaller boat sizes such as M12 and M14, we can make the holes should be around 1 mm bigger. But when it's bigger than that, we have to increase the hole. Now let us look at bearing. Bearing type boats for structural use are available in a large range of species, strength, or grade. The commonly used grades are 4.6 and 8.8, 4.6 and 8.8. Now, the grade 4.6 are common misty and sometimes referred to as the black boats, while the grade 8.8 they are higher in strength, and the first number refers to the ultimate design strength of the boat, and the second number gives a multiplier to get the use stress. For example, if we have a grade 4.6 boat and it has an ultimate tensile strength of 400 Newton per mm square and a use stress of 400 by 0.6 equals to this. So this is the use strength. Let us look at this now. Let's design this boat. We want to design the tensile capacity of a boat. The formula is given with this FTRD equals to 0.9 FUB AS over gamma M2. Now, the initial the design tensile capacity is 0.9 times FUBAS over gamma M2. And I told you that the FUB is the ultimate tensile strength of boat, while the AS is the boat tension area, while the gamma M2 is the partial safety factor on it, 1.25. Now let us look at the tension area represents the area of the boat at the root of the thread, and so it's less than the nominal area of the boat shank. Now, the commonly used sizes of standard metric boats, the tension areas are given in this table 11.2. That is for 12 mm, the tension area is 84.3, like that. These are tension area for different boat sizes. Let us look at a simple example. Let us look at how many boats will be required in this particular connection. Let's say this column holding this column holding down boats. Now, in figure 11, this shows a column which is subject to a design uplift force of 200 kN. Uplift of 200 kN. It is held by 4 grade 4.6 boats cast into a concrete foundation. What boat diameter is required? So we want 4 boats to carry this particular member. How do we go about that? The first thing is, since we are using 4 boats, we have to divide the load that is going to carry by 4. That means each boat will be carrying 50 kN. So load per boat is 50 kN. Then the next thing is we calculate our design tensile capacity. Mind you, the formula for design tensile capacity, as we said the right time, is 0.9 FUB AS over gamma M2, where FUB is the ultimate tensile strength. So using that formula, we put the value out 0.9 times this times AS over 1.29, which will give us 288 AS. Then from there we calculate our AS. So I don't know, maybe I should do this calculation out, I don't know, but just put the value, substitute the value from this place, and then since you you have that, you can always calculate what you have here. So Any question? I don't even know what to say again. Any question? Please look at it. If there's any question, kindly put in the comment section. I will be sending this note to you guys so that you can read more on it. And I hope everything is clear. All these ones, they are basic formula, and it's the same thing that will be applying. So the read. I will stop at let me stop at this place, or let me see. I will stop here. So let me stop here for now. So I will send this note to the class. Okay, let me just say I'll send everything to the class. So you read the note, then if there's any question, let me know. I wish you good luck. Thank you.